All right, welcome back. I'm gonna do a quick review on Kepler's laws, and then I'm gonna end it. I did last in one of the last lessons say that I might try to put all Kepler's laws, and energy momentum. It's too much, so I'm gonna just do a Kepler's law, maybe 15 minutes, hopefully, maybe 20 at the most. I don't think it should take longer. And then the next lesson, I'll begin with the energy momentum, angular momentum. All that sort of stuff. All right. So Kepler's laws. Remember the general idea of Kepler's laws is just the idea that not there are no circular orbits. All orbits have some sort of eccentricity. Sorry, that are to some degree elliptical. This would be considered a highly eccentric orbit. The center, for a our minds imagine that the circles with the sun right in the center. We're talking again planetary motion, right? So more than likely, we're referencing a sun in the middle, um, and planets like ours going around them. And we like to think of them the way we, in first grade were taught. And I'm being honest with you, it's really close to that. It's like 99.9% like that, like for most. So I'm not saying that's not right. I'm just saying that there are many, many billions of stars out there that do not, and surely solar systems that do not have all these nice tight circles like we have. Um, and we can see that with all of our comets, which have these very long elliptical paths. We can see that with Pluto, which is why we don't want to consider it a planet anymore. Out there, there's plenty and plenty of orbits that are not circular. That is the main idea of Kepler's first law. No circle, no orbit is perfectly circular, that it's orbiting directly in the center. He says, no, not correct. He says, even if it's not a hugely elliptical path like I just erased, even like for Earth, that if the perfect center again is right here, that our sun, that actually it's not a circle and that it's an ellipse, even for Earth. This is Earth's orbit. Earth's orbit. And he says, actually, there would be, since it's an ellipse, there's two foci, one here on this side of the center and one here. The closer it is to a perfect circle, the closer those two x's, the two foci, get to the center. If it becomes a perfect circle, then both x's merge into the middle, and the foci is both the center. But otherwise, he says, no, that's not even possible. In all orbits, the sun will actually be not in the middle, but somewhere at one of those two foci. And so for us, our sun would be slightly moved to the side, like I'm showing. That little dot right there might be the actual geometrical center. It's not right there. Is what he's saying. Your sun will always occupy one of the two foci. And then the idea is that the more you squish this thing, fingers or if it's a balloon and just compressing it, then it's going to shoot out the left and the right side. Then those foci get wider and wider, apart. They move closer and closer to the edge. So back to our much more elliptical, um, the foci now are way out there, like this, right? And so if this was our sun, which again has a bunch of nice circular planets going around it, right? Our solar system is in there. All the little dots are like our planets. We have comets that are like, go out on these huge elliptical paths and take like literally hundreds of years to go around their orbit. The orbital period could be a couple hundred years, 75 years for Halley's Comet, things like that. So anyways, the bottom line is this is an idea. Usually when Kepler's laws and the idea of orbits that we're talking about come up on the AP exam, usually they're showing you an image similar to what we have right here. An elliptical orbit with the sun, they're going to color all those circles. I'm just pointing out all of our planets would be in there. They'll just show the sun like this, and they'll show a little elliptical thing, and then they'll probably reference it going around this planet, or maybe they'll call it a comet. Comet goes around, comet, and it goes through point 1, point 2, point 3, point 4, and let's just leave it like that for now. What is the direction of the gravitational force at point 1? What is it equal to? R would be the distance now directly from the sun, directly to the comet. It still can be used at any given point in space. The force between those two Or I meant like as something orbits, regardless where it is, at any given point, if you freeze time, the gravity force it feels back to the gravitational object is still equivalent to in magnitude gmm over. Direction is the gravity force pointing still towards the sun, because that's what suns do. They pull things straight towards them, regardless where they are. At point 2, which way is the gravitational force? Technically, should this vector be a little bigger, a little longer, a little shorter than before? Yeah, it should be a little shorter, right? Why? Well, gravity gets weaker, right? This is equivalent to the formula. It's inverse, gravity force is inversely proportional to r squared. It's called the inverse square law, right? So greater distances are, which this point out here is certainly further away. I'm drawing a straight line, but certainly further away, right? So the gravity force would diminish, right? And certainly we could keep doing that and say here, which way would the force be? It would be straight towards the sun, but it'd be like a tiny little vector. Just barely see it there, but here's our another point, and there's a tiny little FG. There it is. And then after it comes around that point, what would start happening? It would start increasing again, right? And yet when we're over here, it might, too close because I'll just draw a vector that goes straight through the sun. But when we're over here, it would be like, whoa, it would be really, really large gravity force, right? So that's the concept. The gravity force varies, right? It's small at the force between the gravitational force of the sun. It's really the force of the sun and the comet. It's a mutual force, Newton's third law. The asteroid and the sun both pull on each other with the same force in opposite directions. I don't think they'll mention that, but what is the direction, the force that the asteroid uses the sun? This way, right? The sun's being pulled straight towards the asteroid. Why does the sun not move towards the asteroid? It's a Newton's second law there. It's got too much mass, far too much mass. And the change in its motion is minimal, because change of motion like acceleration is inversely proportional to mass, A equals F over M, right? So huge masses, they're not going to move that much from that kind of force. Opposite is true for the asteroid. It's got tinier mass. A is inversely proportional to M. Small mass for the asteroid, rather. Large accelerated motion over time. Generally speaking, that's just the idea. So again, the force gets weak as it goes out. The force gets stronger as it gets close. What about the energy? Where would this thing have greatest potential energy? Remember that I, in another lesson, pointed out the potential energy, gravitational potential energy, which you usually use as mgh. We only use that formula for on the surface of the Earth when things are being lifted up a straight distance to a height h above the ground. In planetary motion, not useful. You have to replace that with something that is more in the form of Newton's universal law for gravitation. I always put that just one on the denominator. Is there a negative there? It is. Don't worry. I talked about the negative. Don't worry about it. It's not important. The bottom line is, because the negative could throw you off. You're like, oh, closer. It's a lot of potential energy. Is it far? Get rid of the negative. It's not important again. Just think of potential energy, right? It always is great when you're something, because you will fall a really far distance and have that potential energy turn into kinetic energy. So where's the maximum? Way out here, right? U is maximum out at this position here. Does it stop at that position? No. Which way is it moving? It still has a tangential velocity to the side there. Still has some kinetic energy. In fact, in that position, the kinetic energy would be minimum. It would be moving slowest. It's like a basketball, that you throw at the very top. It has the most potential energy, but its speed would be the least at the top, right? So that's the idea. And then as it comes around that corner and starts heading back towards the sun, what's going to happen to the potential energy? That potential energy is going to start transforming into kinetic energy, right? So you'll have, much more kinetic energy here, you'll have more kinetic energy here, and you'll have less potential energy compared to this position, right? The potential energy will go down as it comes around this and moves to this point here. Potential energy will decrease because it's getting closer on some distance and transform some of that potential energy to kinetic energy. What will happen to the total mechanical energy of the sun asteroid system? Total mechanical energy of the sun asteroid system is still just U plus K, just like always, right? So in between those 2 points, the ones that I'm talking about, the one that's all the way on the right side of this diagram and the one that's right there. How much will the total mechanical energy change by between it as it moved from that point to the second point? By none, it won't. There's no way in outer space. Like, we make some approximations again in our physics about like mass moving systems, and like, yeah, but in the real world there is some friction and there's some air resistance and things like that. There's some heat that's created. And the total mechanical energy doesn't really stay exactly the same. There is always some energy to the environment. Oh, but we don't talk about that a lot in introductory physics, right? You're familiar with this. In outer space, how is it going to lose energy? How is it going to lose energy? There's nothing out there. There's nothing out there for it to interact with. The only things that are out there to interact with are them themselves, gravitationally. There's no air. There's no way you can't have friction, can't have air resistance. There's nothing for it to interact with. So in this case, it literally is true. Like, the total mechanical energy of the system, potential plus kinetic, goes round and round that orbit, always stays the same total. Think of it as kind of like a ball, in a bowl. You have a bowl and you let a little marble down. It goes boom, 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 back and forth. Imagine no friction, no air resistance. Keep going back and forth forever, back and forth. It would have maximum potential energy up here, and then I would have all of that would turn into kinetic energy at the bottom, and then it would just return to the top with the same amount of potential energy, the same amount of kinetic at the bottom, back and forth, round and round, and things would go back. That marble will go back and forth. In the real world doesn't, because there is some friction. But that's the idea here. Round and round this thing goes, always maintaining the state of energy, total mechanical energy, right? That's an important idea. They'll probably ask you about that. See if you know that. So now let's continue this picture, draw some more pictures. Now, let's just delete. Let's just draw again. So here are, so again, we had like 1, position 2, position 3, position 4, position 5, position 7, position 8, position 9, position 10, position 11. So at what position will again, this is all these positions represent some point in time where there's an asteroid there. And it starts here and it goes that way. At what position will the asteroid have the greatest kinetic energy? Whenever it's closest, wherever it's the closest approach. So in my picture, which I didn't draw very well, the closest approach is actually always here. I know that this one might look, if you did a real ellipse with like a real machine that you can use to make perfect ellipses, the closest approach, called perigee, is actually over here. Perigee is over. You don't have to know that word, but that's what perigee is. Perigee is the small, like periwinkle, like you've heard periwinkles before, tiny, small. So it's actually on that side. This is the closest. And so if it's the closest distance over here, then it should have the maximum amount of kinetic energy and the minimum amount of potential energy, right? On the apogee side, which is over here, again, you don't need to know that word, but it's apogee, A-P-O-G-E-E. On the apogee side, that's where it's furthest away. This meteor or this comet would be furthest away. So this is where you'd see that the opposite's true, right? The maximum potential energy out here, minimum kinetic energy. Is there anywhere where it stops? No, it's always motion. But there's this trade-off, continual trade-off between potential and kinetic and potential and kinetic. What does the total mechanical energy do? Constant. They would say total mechanical energy of the sun asteroid system. Check. Let's talk. That was that was Kepler's first law again. That all things have elliptical orbits to some degree, and what's called the eccentricity of the orbit. This is a very highly eccentric orbit. One that's not. This might be like 98% eccentricity. This one might be like 0.1% eccentric. And the eccentricity varies for planets and different things in outer space that are all orbiting around stars. But he just pointed out that you can't make that bottom one become 0%. So for Earth, it's like that 0.1 or something like along those lines. But like for things like, these comet paths, it might be like 98% eccentric. And that percentage just gets higher and higher, 99, 90.98, 99.99, 90. Can't go over, can't reach. 100%. That's the general idea again of Kepler's first law. Kepler's second law, best just to show it here, right? Um, Kepler's second law was right here because I thought this is, easiest way to review it, just to see it again. The idea was that as this thing its path moves, it sweeps through equal areas. So the area of this purple triangle that I'm pointing out right here as it moves from position 0 to position 1, and let's just say that was 1 day. Let's just say, in the real world, it would be much less, much more than 1 day rather. It takes usually hundreds of years for these things to go around. But anyways, let's just say it was 1 day. In the first day of moving from here to here, the area, it sweeps out this area in 1 day. Day 1 to day 2, here is now Tuesday or something like that. It's this area of this other one is the same amount of area as this one. I know might not look that way, but yeah, this one gets stretched further, this first triangle, but it's thinner. This one gets stretched wider, but it's shorter. Turns out when you geometrically and actually work it out, the areas, the same area. And on Wednesday, it moves from here to here. Right? And that's not saying that it moves the same arc length. This arc length is shorter. This arc length is longer. This arc length is even longer. They're not equal. Things that are equal is the full area it sweeps out per day is equal. And over here, that thing zips around. So these things, again, if you're watching my mouse is the asteroid, the comet. Slower, 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 like slower, lower, lower, and then it starts to pick up some speed. Faster, faster, faster. That's why these lengths get longer. Faster, faster, faster. And it whips around the side and slower, 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 and it repeats. Right? But the second law is that in equal intervals of time, okay, like I had used, but whatever the time is, doesn't matter. It will any um, if this is weird. I actually have a student that is logged in. I heard boom, which is weird. Um, they might have, might have thought that it was weird because I'm actually in one of my classes. Anyways, I mean, you can come back if you want to. Probably just a little surprised to see me here. Anyways, so if this is the comet and the gravity force is a vector like this, um, technically that can be broken up into components. In fact, I'm not sure if that's the best spot to draw it because it might be hard to draw those components. But the bottom line is there is maybe let me try to think about that. It's easier to draw it over here. So like maybe over here, it was easier for me. So this would be the gravity force. And then there's components there I've drawn. And notice that this bottom one component technically should get some torque. In fact, still not even sure if that's the best way to draw it. Because R goes this way, right? R goes towards the sun. And you would actually need to have a component that goes this way. I think you can. I think it works something like that. I'm not 100% sure. I think that's how you draw it. The bottom line is if this thing was coming along this dotted path that I'm making right now, and this represents the gravity force here, there is a component of the gravity force that's perpendicular right down here. And that does create some torque. And that torque is actually what accelerates it at that, because we saw it whipped around. Well, that means the rotational speed increased, angular speed, right? And angular accelerate. There was acceleration, or speeds up in its rotation. That comes from the geometry of a ellipse, where when you break up the gravity force vector into components, you can sometimes, yeah, it takes a little bit to try to figure out how to draw it, but you can break up components however you want, as long as it forms the right angle. And you can realize that there is some component that's actually, like I've done down here, of the gravity force that's perpendicular to R, which again, it's not part of the same diagram anymore. I just made a new one. Assuming that now I'm referencing this is the sun here. That this component actually provides some torque and causes its rotational speed to boom, whip around and really speed up. And then as it goes further and further away, that component gets tinier and tinier and tinier, which means there's less and less torque. And the less and less torque means that its rotational speed actually starts to slow in its rotational speed. All right. I don't think they'll mention that. I really don't. All right. The very last thing, and then we'll be done, is Kepler's third law. Kepler's third law is just that the square of a period, orbital period, is proportional to the cube of the orbital radius. And so something he discovered that when he looked at all of the planets in our solar system, that this was true for all the planets. That if you took any of our planets' orbital, which all of our planets don't go around in 1 year, that's just Earth. As you go further out to like Jupiter, Saturn, Uranus, Neptune, Pluto, those periods get longer and longer and longer, because not only are they moving slower, right? Because we remember that the orbital speed is inverse. So when they're really far out there, not only does their speed decrease because the gravitational force is less out there, but also because their orbit is just so giant, right? It's going to take a long time to get. So they're there, much more than 365 days, of course. But the is he realized that no matter which planet you picked, if you found out what the orbital period was for that planet, squared it, and then found out what the radius of that planet's orbital radius was, and cubed it, and compared those two answers, they weren't equal to each other, but that they were proportional to each other. And then he would have to take another planet and say, okay, if I have another planet that has, let's say, because before I say that, if we were to move that over, we would just square root both sides. Remember, square rooting is the same thing as raising to the 1/2, which means, and when you do that, you have to multiply your exponents, right? So we'd end up with t to the 2/2 equals r to the 3/2, which is really just t is proportional to r to the 3/2. So what he realized was that, which by the way is just 1.5. So the period of an orbital period is proportional to r to the 1.5, interestingly. So he realized that when he found a planet that, let's say, was twice as far away, like Mars is pretty much almost 2 AU, and we're 1 AU, that when you take Mars, which is 2 times further away, its orbital radius is 2, and you go 2 to the 1.5, or you can think of it as 2 cubed, I guess is another way of thinking of that, and then square rooted, right? So 2 is 8, and then the square root of 8, I don't even know. Can't be 3. Less than that. So square root. I got 2.82. So again, he found a planet like Mars that was twice as far away, plugged it in like we did in for r, raised it to the 1.5 or 3/2, and the answer comes out as 2.82, which means the period should increase times a factor of 2.82 for Mars compared to us, because Mars was, again, 2 times further. Not twice as much period, twice raised to the 1.5 as much period, which comes out as 2.82 times. And then when you look at Mars's period, and you literally take our period of 360 and multiply it by 2.82 on my calculator, 1,029 days, and you look up Mars's, it's exactly correct. And it's not just true, it's true for all of them. It's true for the whole system. So we discovered, that there was this mathematical pattern connecting period, the time to get around one full orbit. We usually call that 1 year. It's not necessarily the same amount of days for all planets, not by any nation. Um, Even if it's a 200-year Pluto orbit, then 1 year for Pluto is 200 years, and that means there's you know winter, potentially winters and summers just like us, right? So a quarter of the year for us, thank goodness, is only what, like 3 months. Well, if you're at two, 200 years, a quarter of 200 years is like 70-year seasons. So like, I hope you're not born in the beginning of winter. If you're a Plutosian, I don't know what you'd call them, but your whole life would be rough. That'd be like a punishment. Anyways, this is the idea. There's that relationship. Sometimes you will see it written like this. To be honest, I don't think it's necessary. You'll see like comparing two planets in the same solar, the period of the second divided by the period of the first planet squared is equal to the orbital radius of the first planet divided by the radius of this orbital radius of the second planet cubed. Notice the twos are opposites, the ones are opposites. It's just not, I find that students are more confused by this because you don't need this representation. All you need is the proportions, which we do all year. All you need to answer their questions is that t is proportional to squared is proportional to r cubed. That's what I remember. And I can always think, oh, okay, take the square root of both sides, which is again raising to the 1/2. All right, so t, work it out. All right, t is proportional to r to the 3/2, or 1.5, and that's all I need to answer their questions. When they say comparing two planets, this planet has a radius that's greater by orbital radius that's 5 times greater. But is its period greater for this new planet that has a orbital distance that's 5 times further away from the sun than the other one? Just 5 to the 3/2. Just plug it into your calculator and hit enter. That's it, right? Whatever comes out, that's how much longer its period will be. 5 cubed, 25 times 5, 125. Square root 125. In my case, I get 11.1. So that means the T2 for this planet that's way further out there, 5 times further out there. 5 to the 3/2 times T1. Its orbital period will be 5 times further. Well, 5 and 5 raised to the, I didn't mean to say 5 further, 5 raised to the 3/2, which numerically, do they ever put new numbers in their problems? No. And their answer is no. Numerically, as I just did it, it was 11.1 T1. Are they going to show that? No. You know how they are, right? Everything's exact. Everything has to be exact. But that's it. That's the idea. As long as you know that t squared is proportional to r cubed, and that further away means longer periods, and that closer in, like Mercury, means shorter periods. I guess lastly, know that, again, t squared is proportional to r cubed, or even better, this format, t is proportional to r to the 3/2. And then know if they decided to do this kind of thing with you and say, what would this graph look like? This is 1.5, right? We know what t is proportional to r squared looks like, just a parabola, right? We know what t is proportional to r, which is r to the 1, looks like, just linear. So where must the 1.5 fall? This is r to the 1. 1.5 must kind of be in between the two. There it is, r to the 1.5, right? It has to be in between the graph that's linear, r to the 1, and the graph that's squared, because that's how math works. It's in between two numbers, and its graph needs to be in between the two graphs. Right? So this is just pointing out, if they gave you a period versus, for a given solar system, what is the period versus orbital radius graph? It's this one right here. Right there, still has this kind of upward curve to it. Right? And remembering again, v, orbital velocity versus radius, looks like that. Further and further away, less and less orbital speeds. All right, guys. I think I finished what I said I would, which was Kepler's laws. So at this point, I'm done with dynamics. What an achievement. I am going to pat back. And I'm going to pat you on the back for working hard and continuing to watch these because we're almost there and it will all pay off for you. So next one, I don't know that I'm going to do any more today. You can see it's what 11 a.m. on Saturday. I don't know that I'm going to do any more today. I think I've got enough. I mean, I know I've got a lot of you, and um, it is what it is. It is what it is. We've got videos that I'm giving you, giving you some obviously some problems to work on. So a few hours each day. I don't think that's crazy for an AP student, especially when you guys have only one AP. I think almost all of you. I don't think there's any other AP class that's conflicting with this AP exam that we have on Wednesday. So over a weekend, 3 hours on Saturday, 3 hours on Sunday. Yeah, that makes sense to me. And I'm sorry that I'm not trying to make little minimize it. It's a lot. It is, but I'm just that's what that's the world of AP classes are, especially right before an AP exam. So I'm hoping that you're finding this useful. I know that you are, and that we're almost there because again, the only other thing I'm going to require you to watch after this is the energy and momentum. I'm going to try to get that into 1 hour and 15 minutes. Both of them, energy and momentum in 1 hour and 15 minutes. And then the optional ones after that, rotation and simple harmonic motion will be optional, right? But for me, I get to take a break for the remainder of the day. And I will see you next time. Bye-bye. Or I didn't say it right. See you soon.